Большая зеленая кнопка есть. Это мы знакомимся с техникой. Всем привет. Меня зовут...
This is us testing the microphone. Okay, it seems to be working. My name is Sergey Gordichik, and together with my co-conspirators, we are going to talk to you about our research. But first of all, I need to start with a magic word. It's QR code. This is a very important QR code that you need to read it using QR code software. And those of you who send us the craziest question will get the craziest software. If you do not send your crazy questions to us, you will never get the crazy merch. We also have a microphone in the room. You can use it to ask your questions here directly to us. But QR code is an excellent technique. COVID is behind us, but the QR code is still here. Let's get started.
О чем мы хотели сегодня рассказать?
Here is what we wanted to discuss today. Yeah, it looks like a boring topic. This is how you do my map for 4,000 addresses and get excellent results. Seems like something straightforward, but depending on whether you know how to do a map, you can get different results, like 7 million services that are in Russia. You can be converted into 20 million using certain technical tricks. Let me introduce actually, you know me already. My name is Sergey Gordichik. That's me at the bottom. Next to me is Alexander Chernenkov, Anton Shmakov, and Alexander Gurin. We are all from CyberOk Studio. We'll start with something trivial, TCP scanning. It's very easy to scan TCP. You send a packet, something comes back. If something comes back, then the port is open. Nothing comes back, the port is closed. The problem is to scan 65K ports to make sure that you scanned everything, and that's too expensive. You need to send 65,000 packets. But if you take 47 million IP addresses in existence in Russia, and you multiply that by 64,500 ports, that will mean
Поэтому большинство глобальных систем ISN, типа Shodan,
307 billion packets that you need to send. And the available tools like Shodan can scan 1.2K ports. Census can scan 3,500 to 5,000 ports, depending on the country. So there is this limitation. How do you overcome it? How can you scan TCP ports actively and frequently, get the banners, but not kill the internet by sending all these billions of packets out? And not to kill your own budget by buying the services from providers. Well, the providers, of course, will be very happy if you bought all of the services, but we do not have limitless wallets. We've been working on this issue for a long while. It's a long list. There is no need to read everything. If you're watching this presentation offline, then you can refer to the slides. There are several techniques that deliver good results and that enable you to save 90% of the traffic. I'm going to discuss them a bit later, but let's start with the first project. It's called Smart Probing. Gradient boosting is used. The execution is quite simple. It highlights top 20 ports that should be scanned. We'll understand that per node, well, if my memory serves me right, on average, there are about 4 open ports per live node. If there are more than 15 ports, that looks suspicious. More than 50 ports, most likely it's a honeypot, and we're going to talk about that later. Smart probing here allows you to select the most efficient approach. The only thing for smart probing to work, you need a lot of information. And the next step, when optimization has become workable tool. This is something we talked about during the last hack days. GPS, Senses, Smart Map. Those guys produced this solution. It didn't work very well. Ground roof, the 64K scan results across the whole range of IP addresses were put into a matrix. 6 billion IP addresses, 64K ports. They were put into a matrix that computed probabilities. What's the probability that this or that port is open on this or that IP address? So basically, this is a workable solution. It's just that since these guys are from American universities, they had unlimited access to Google Hub. But when we tried to replicate that on other resources, even subject to all optimizations, it didn't work because the matrix was too huge. After that, a publication came out from PMAP. PMAP suggested a more rational approach from our point of view. Most likely, many of you are in bug bounty or you're familiar with, you know that every network has its special features. In ISN, there you understand which ports are open, more or less. If it's an ISN with the client devices enabling internet access, that's one thing. If it's an ASN with reverse proxies, for internet providers to publish web resources, that's something different. A PMAP approach that they declare in their work boils down to the following. Per ASN, several nodes are scanned randomly, profiles are built, and after that a graph is built that you use to select which of the ports you need to scan next, most likely. You scan it, and depending on the output, whether it's open or closed, you rebuild the graph. They called this reinforcement learning in scanning because ideologically, well, it's a good name. Because if the system guessed the port correctly, you confirm that choice. So it's just a regular algorithm, not real learning. Anyway, when we try to implement that, the scheduler which determines which port should be scanned next, it takes more time, takes more resources than the regular scanner. At 10 megabit, you send 14 million packets a second, so 14 million a second. You need to take the decision as to which port needs to be scanned next. We thought that these guys had some magic. We tried to get in touch with them. We tried to understand how this graph is rebuilt. But it turns out that they never tried to implement the algorithm. Well, maybe they did try to implement it, but it looks like it's paper engineering. It's just, sometimes scientific papers are like this. It's just a paper. It's just a publication, theory, rather than practice. IP-REDS. IP-REDS is a combination of approaches that was suggested by GPS and PMAP. You split the network into a smaller network, subnets. You use classifiers. You build a Bayesian classifier, and then you use matrices, not for the whole internet, but only sparse matrices. And this approach not only predicts ports, but also protocols. Here you see some of the formulas for you to understand that this is a funny presentation, an exciting one if you're going to read this offline. This picture especially for you. We implemented this approach with some updates from us. And this is how it works. You also need ground roof. You need to get some results from the internet scanning all of the internet, but on top of these results you also run a script that will deliver subnets and the ports that are most likely open on the subnets. We're going to publish this script very soon, most likely next week. You will be able to use it in your own tasks. The more this ground truth you collect, the more scanning results you have, the more precise the algorithm becomes. But of course, you have to embed the outdating algorithm as well to let the algorithm know that some of the data may be old. To get accuracy of around 98%, that is to say, to get the probability of 98% of determining the port that is open, you have to embed a deviation of 1 to 2% of topic scan. Not 3,000 packets per node, but 36 packets per node will suffice. And because the algorithm also shows you the networks that need to be scanned, not all of 46 million IP addresses in brunet. In brunet, you need to send 60 times less packets. So again, the algorithm will be published soon on GitHub. Go and use it. Some more curves showing you conversions. The yellow line is our brute force scanning. The blue line is prediction from our algorithm. Around 100 ports, the convergence is already pretty strong. Now we are scanning about 100 ports per node, and this gives us high probability, close to 99%. 99% of brute force accuracy. We're also growing our own little passive DNS. Why do we need it in the system? To enrich the results, the match of IP addresses and host name, and to expand scopes of scanning. For instance, if we scan HTTP by IP address, we are going to get one set of results. If we do scanning by host name, we're going to get a different set of results. 2 million to 67 million of web services on brunet. This will be your difference if you take into account the host name. There is a little bit of machine learning embedded. There is also the public version that we used. The link is at the bottom of the slide. What's interesting, and it may sound quite obvious, but during our work, we came across an anomaly in DNS services. There is a standard KIN DNS where you register, and then there are specific KIN DNS services, some IP addresses to which hundreds of thousands of domain names point. And one of them is quite curious, kinetic DNS. In your device, you can tick a box, it will go to the internet, it will issue a certificate, and it will lead your device outside. So we dug a little bit deeper, and it turned out that 173,000 live services utilize a dozen of addresses, Kinetic Pro, Kinetic Link, etc. And most of these devices are network device control interfaces, but they're also used often to publish web apps that probably are behind this device. Kinetic is the new Microtic, looks like, judging by the volume. And our guys yesterday, during their presentation, big and small boxes, were speaking about all these internet-facing devices installed without proper thinking. And now, there are lots of very interesting resources out there. If you Google them or you use Shodan or something else, you will not find them. It's just because they do not know about these domain names.
Bug bounty.
But if you have bug bounty, if you need to understand the attack surface, then
Пойти поглубже. И вот такие
you need to dig deeper. These DNSs, Kinetic is not the only one. Kin DNS, we are going to make a publication soon. But there are many of them out there. And the next part of this presentation is the gold probe, scanning UDP. Well, it's easy to scan TCP, but it's more difficult to scan UDP. So, Alexander, over to you.
Всем привет.
Hi, everyone.
Меня зовут Александр.
Yeah, my name is Alexander. That's me. I'm Alexander.
С UDP, с какими проблемами столкнулись, вот, и чем готовы поделиться в результате.
Now, I'm ready now to share with you all the fun we had with UDP. Let me remind you first how UDP scanning looks like. It's not the same as TCP. It doesn't tell us where the connection is in the handshake. There is no handshake per se. And when you scan UDP, you are primarily interested in a situation where there is a port and you send a probe there and the port returns specific data. And this tells us that
Чтобы просканировать, существует много инструментов. Два самых удобных для наших целей — ZMAP и Mascan.
ZMAP and Mascan, probably heard about them, turned out to be the most useful tools. ZMAP is useful because it's got 28 of its own probes embedded. And then we went beyond ZMAP based on information available at UDPX project and two files where files are stored in the MAP project. We use those. We will be ready to share a tool that, regardless of what you want to use to scan UDP, be it Mascan, UDPX, or ZMAP, to use all these probes from all these three projects together. And then you will get a list of ports, and a bash script can be built that will run across your infrastructure, that will transverse your infrastructure. Mascan doesn't have its own probe database. You will have to find them yourself. It uses MAP payloads, but it's got one problem. If you want to scan port 161 with an SMP probe for version 1 and version 3, the Mascan will scan only the first, with the first probe that will be on the list. It means that you will be losing information. So the tool that we will be willing and ready to share will let you use different MAP payloads files. They have different level of priority based on the map. It was not going to be a big one file of payloads, but instead this will be a file containing probes that with a higher probability will be able to get responses from the ports with a higher priority. Of course, from the perspective of the MAP developers. This tool in the MAP payloads format for Mascan, this tool allows you to get probes from MAP and UDPX projects to, again, extend the scanning range, and it also allows you to overcome this Mascan problem, which is one probe per port. UDP scanning is not the most interesting thing that you can achieve with UDP. It's the data analysis. That's what matters. The first thing we did was build this very complex matrix. We tested all probes that we had on hands. And this matrix, we colored it with different colors. We got a heat map, and it turned out that some probes get responses not only from the ports for which they were intended, but also for some from some non-standard ports where the service shouldn't be in the first place. The gold probes, it turns out, were Citrix from a map, in addition to 1604 port. In these statistics, you don't see it virtually. Actually, it collects a lot of responses from the non-default ports from this service. The same behavior was demonstrated by L2TP probe and also SIP options. It looks like an HTTP request, in fact. And the IKEY main mode probe
частью протокола IKE.
is part of the IKE protocol. And another probe, DNSSD, this is a service discovery probe. It also showed behavior where it collected responses from the ports that were totally not supposed to answer these queries. Here you can see the list of those probes. They are the golden ones. You should use them as such. Why are they convenient? Because there is greater probability that these probes will be able to get you responses from ports, all kinds of ports, non-standard, non-default ports. So you don't start with anything else before you run across your infrastructure with these 4 probes. As a next step, well, we collected the data from scanning, and we need to analyze that. We found 2 types of anomalies. One anomaly was big number of hosts that, if you send a probe to this port once, they would return 100 to 1,000 and sometimes even more, hundreds of thousands responses. This called our attention because it gives you the potential for a UDP amplification attack. And another one is big banners that come back. The LTU of 1,500 bytes, we couldn't go past that, but big banners, of course, they engaged our attention. When we are saying that we would like to test whether our infrastructure has any misconfigured services, there are 2 approaches. One is rather fantastic. You can remember all the host services by heart and how they are configured. And the second approach is more realistic and more natural. I think it's when you scan all your services yourself from the outside to test their behavior. And for this, we are using another tool. We're going to share it as well. It lets you scan your own, scope your own infrastructure to answer the question whether your infrastructure can be abused by an attacker to amplify DDoS attack using DDoS. This is the most interesting stuff we found. The NTP probe, which is only 192 bytes size, but it found many hosts that responded up to 100 times by 440 bytes each, which gives you an excellent AMP coefficient. The same L2TP, the same behavior was demonstrated by L2TP probe. The AMP coefficient was 150, roundish number. SNMP, we wanted to test a different probe. We wanted to get a probe that would get us as much data as possible from this port. And we found such a probe. 36% of the hosts scanned port 161 returned a response of 104,072 bytes in size. And the amplification coefficient here is rather low, but because this SNMP service is so popular, this may be a critical component in an attack. We also noticed an ecosystem BitTorrent, right? We selected the top torrents trackers. We send a list, we send a Jean-Pierre's request that can return up to 100 neighbor ports, and we found several anomalies there. There were groups of addresses that could return 500, 300, 3,000, or 1,300 bytes per response. Again, the coefficient, application coefficient is small, but it can be used in an attack. And there was a host that unfortunately got lost somewhere. I miss it dearly, but there was this address. I was very happy to see it. it responded 368,000 times on per one probe, and you can see here the AMP coefficient. Yeah, unfortunately, it disappeared,
Турман, наверное,
just like Uma Thurman
брюнетки в криминальном чтиве на блондинку.
disappeared.
Что поделать?
She used to be a dark-haired lady in Pulp Fiction, then she became a blonde girl in Kill Bill. Anyway, loop DDoS. CISPA reminded the internet about this problem recently. The idea of the attack is as follows. We've got two servers, each of which responds with the same response to a query, to a call. We can run a spoofing attack on the first server and then send an error on its behalf, and the second server will respond with an error again, and then we'll continue exchanging errors in a loop according to CISPA data. And this is already available in the official publication from CCCERT.
Вендоров Broadcom, Cisco.
Cisco, Broadcom, Microtik, Zixel, they are all vulnerable to this vulnerability. And there is something that we've found that was not in the CISPA report. 8,000 instances around the world, 4,000 in .ru. It's Skipper. The problem is not in the service. The problem is in how UDP stack is configured in this or that service. And in conclusion, UDP may look quite banal. It's a transport protocol that's been around for years, and yet it keeps surprising everyone. DDoS and amplification attacks are still with us. They have not disappeared. So scan your scope, know your perimeter. Don't make your own infrastructure a helper to the attacker. And use the tool that we can share with you gladly. Now I'd like to give the floor to Sergey. No, Anton. Anton. Hi, everyone. My name is Anton Shmakov, and today I want to talk to you what to do next. So you scan the internet, you collect the banners, and as the next step, we need to define the software. We usually use regexes to define the software, but it's so boring to write them, so we thought that maybe we could automate the process. And today I want to share with you two algorithms that we use at CyberOak. The first one, fuzzy hashing, and large language models, LLMs, for them to write regexes for us. Let's start with fuzzy hashing. Fuzzy hashing allows us to look for similar but not non-identical lines and strings. And we decided maybe we can apply this algorithm to the banners of the services that we collected. So our objectives were, we want to find similar answers from the servers, the banners, to cluster them and to define the software. Then we need to identify the typical interfaces like administrative panels, or we like to find all phishing websites in brunettes because we know that they are built according to the same template. And there is another task. We want to use algorithms to analyze the collected banners, to perform deduplication, and to optimize the scanning process.
In the course of our research, we researched some fuzzy hash algorithms, identified their advantages, disadvantages, and we also calculated the optimal value for every hash and algorithm. So the question is, what's next? We used the graphic database management, data storage, and this is the evaluation of the similar services. This slide shows the request received by our database with the SSDIP evaluation. The one cluster is highlighted in blue, and a larger cluster is highlighted in red. But what if we increase the similarity ratio up to 90? We only have fewer nodes in the blue cluster, while the red cluster has been broken down into several sub-clusters. So let's take a closer look at what's inside. As you can see, these are GitLabs, which are very similar, but they are not the same. Highlighted in red are the differences between GitLabs, but the clusterization problem was solved, and we're going to use it to look for new software pieces. This tool can be found at our GitHub page, so please subscribe to our Telegram channel and stay tuned for new announcements. Now let me move on to the way we actually automate the process of generating regular statements. First and foremost, we want to get new products, so we want to add it to our toolbox at a minimal cost. And we also want to free up our time to do something useful, for instance, doing some additional tasks. What we started our research with is as follows. The source was the work project where people used Roberta. It's a custom trained HTTP heading model, and they got embeddings as an outcome. These embeddings were then clusterized with the help of the HDB scan algorithm, and then the researchers used the algorithm of finding the same sublines in the local subclusters to generate regular expressions. So we read this article, we took a closer look at the way it works, and the results are shown in the next slide. So column 1 in the table shows the HTTP heading singled out by the model. The second column shows generated regular expressions, and the third column shows the desired outcome from this process. In other words, it lists the best generated expressions, because the original model generated suboptimal garbage expressions. It doesn't take into account the version, and actually we wanted to generalize everything. So we decided to introduce a number of changes manually. The first thing we did, we identified the whitelist of HTTP headings such as server X powered by X CMS version, and so on. Secondly, we added the analysis of the title tag content. It's a must to be able to identify titles of software programs. Correct me if I'm wrong, oftentimes administrative taskbars use their own headings and even versions in their titles. And to double-check the automation process of the generated expressions, we used the cat boost algorithm, and we also fine-tuned that at the last stages to make these regular expressions comply with our format. So we scanned the entire row segment with the help of 3 ports. We generated about 100 new regular expressions. Based on that, we identified 789,000 new services that we did not see before, and all of this took us about 6 hours. That brings me to the end of my part of the presentation. I'd like to pass on the floor to Alexander. If I may, I'd like to add a few words to that. The previous parts of the presentation were devoted to how to scan less and get more results. But now it's going to be just the opposite, how to get fewer results. Because if you're doing mass scanning or mass probing, sooner or later, you will come across honeypots. They exist. These are not myths, and the problem with honeypots is that they just kill your results basically. They add too much garbage. Well, you're not going to hack them, but it's going to be difficult for you to work with the outcomes because you won't be able to discern between true and false results. We came up with a classification. There are blonde honeypots. These are simple honey traps, and when they receive any request, they just send out some garbage. All 65K ports will just get a banner, and that dilutes your results. And Uma Thurman demonstrated in UDP was just a honey trap. The brunettes are low interaction honeypots, and the redheads is another category of honeypots which we're not clear on yet whether it's a category of real services or this is the way they behave. Maybe they're wearing green dresses, and Alexander is going to give you more details on that. Hi everyone. Right. What is a honeypot? Honeypot is a set of technical and organizational measures that serve as a lure for an attacker to identify, to ensure early identification of an attack on an infrastructure with the help of a behavior analysis. Honeypots have been developed for 20 plus years, and the first such solution was the HoneyD. The peak was seen in 2017 and 2019 in terms of honeypot development. Right. Honeypots can be broken down into several categories, and they include databases, SSH, Telnet, VNC, management protocols, email servers, various web apps, SCADA, ICS systems, IoT, and blockchain. There are lots of them. They are in demand because they cause much damage by PAHEC, but I'm not going to touch upon that because it's a subject for a separate discussion. As was mentioned by Sergey earlier, the interaction levels could be low, medium, and high interaction. And we just call them blondes, brunettes, and redheads, or gingers. We are not being sexist. Sorry, ladies, if you take an offense. When we researched the honeypots, we saw a RIP in GitHub, and over the past 9 years, quite a number of honeypots were added there. But in this bunch, we saw lots of legacy honeypots. But nevertheless, we did identify some useful things. In DocHub, you can also get info on some of honeypots and then use it. These lists are, of course, interesting, but in RUNET, we found an even more interesting thing. And by the way, I'd like to thank Bastion, which last year collected and categorized the greatest number of honeypots. I insist that you take a closer look at their list. They did a great job, and like I said, we appreciate that a lot, because their post helped us a lot in our research. Based on all of the above and based on the outcomes of our research, we came up with our own top 10 honeypot lists that you come across in RUNET most of the time. As is clear from the slide, most of these honeypots are obsolete. They have not been updated for a long time, and you can detect and develop systems like that without any limitations. We decided to take a look at what our counterparts do, and this is the statistics on honeypots in different ASM systems. At the present time, ASM systems are not very good at detecting honeypots. For instance, Shodan is not really alive and kicking at the present time, and Shodan has become a benchmark of sorts. Therefore, we're going to use its functions for benchmarking. Shodan is greedy, but info on a honeypot on an IP address can be received from the IPN-BD, and you can use this function to automate. We can use this function to automate our research. By using facets linked to API, you can get the list of honeypots from Shodan, which you cannot see through the user interface. And Shodan, if you use the hash specified in the slide, can detect such honeypots as Covery that existed 4 years ago. By the way, this is the most widespread Shodan honeypot from the viewpoint of Shodan. 3,800 honeypots like that were identified out of 4,500. So that's the greatest number of honeypots detected by Shodan. As for low interaction honeypots, in other words, blondes, these are the most unpleasant honeypots to scan because they send out too much random info, and that slows down the scanning process, and it also results in recording in the database too much garbage data. The host low interaction honeypot is shown in this slide. Over 800 server headers were sent out by this honeypot. If you run them in the Internet DNDB, you'll see that most of these honeypots are blondes. MMK3 hash honeypots are shown here, and without an internet subscription, you can collect most of the Shodan detected honeypots. We decided to see whether counterparts know about their own honeypots. It turned out that Shodan knew nothing about Netless, FOFA, or other detection programs. Not a single honeypot wants to be detected, and that's why honeypot developers try to conceal them by using various techniques. They use legitimate software, they use domain and subdomain domains in isolated environment. They use clouds. Honeypot users want their honeypots to work and still stay disguised. That's why they can regulate their level of complexity, combine various solutions, in other words, using a hybrid approach. There are simple scripts that generate simple web honeypots, for instance, Outlook Web Access honeypot, which can easily be detected. When configuring honeypots, users can make errors that results in a misconfiguration, and that slightly helps in detecting them. During our research, we came up with the following stack of open source tools that help you discover most of the honeypots. Nuclei, network fingerprinting, HTTPX, and NAB. HoneyDet is an alternative to Nuclei, and Nmap is the classical tool. For a more convenient scanning of honeypots, we developed our own microservice that we called HoneyDtag. We use the body base as a front and the web front face. We also use Nuclei and HoneyDet as a scanning tool because there are multiple flow tools. Exec API is an intermediate between body base and Nuclei. We use MySQL as a database, and we used various other auxiliary tools, scripts, and so on. By combining all of these tools, we developed our own program that we will soon upload. It will be publicly available. Stay tuned to our Telegram channel and follow our public GitHub page. Shodan Honey score will probably rest in peace very soon. As for the takeaways, honeypot makers like cloud hosting such as AWS, Google Cloud, DigitalOcean, Yandex Cloud, and so on and so forth. Honeypots can be run on standalone TCP UDP ports on legitimate IP addresses right next to the legitimate ports, and then they can penetrate sandboxes. ASM competitors know nothing about honeypots of their counterparts. And smart people can tailor-make their own honeypots, which will be difficult to detect without being a magician. And, scanning and detecting honeypots is a real pain. Thank you so much. That brings me to the end of my presentation.
Вот как раз наш телеграм-канал.
Right. This is a QR code to go to our Telegram channel. I do understand that we're really short of time, but we try to brief you on what we did in the field of mass scan in the past year. Every part will be described in great detail in a separate article. 2 releases have already been published, and you can go to our channel and like these publications. Thank you for the questions. There are lots of them in the chat box. I'll read them out very quickly. The first question is, how much time does it take you to scan the entire RUNet? Well, we have 2 traffic flows. The first one is the fast scan. It's done once a day, and the second one is the 65K scan, which is done simultaneously. It takes about 2 weeks. We do that so that we do not kill the network, otherwise the situation might be aggravated. Let me take the next question as well. How do you identify the accuracy? These 2 questions are interlinked. For the algorithm, you need the ground truth, in other words, the results of the 64K port scans, and then you train your model based on that, which means that we need to update this data all the time. The data that we collect within 2 weeks and the data on the most popular networks and ports that we collect within a day ensures the right accuracy. Another question about accuracy. What's the permissible accuracy? Well, I guess it's more of a philosophical question. We follow the expectations of our customers. If we do continuous penetration testing, such as Shotgun, Sirius, and other, if we're more useful than our competitors, then it's a job well done. At least we should not be inferior. As for the practical figures, 36 ports per node ensure 98% of accuracy as compared to the ground truth, and 100 ports per host is the next level of accuracy, which is going to be considerably higher. The difference between 70 and 98% is not that great. So 40 to 50 ports per node is what we scan. The load is not that huge, but the results are still accurate. Another question is probably addressed to Alexander. It's about the single golden probe. Have you ever tried to develop a single golden probe for UDP so that everyone would respond to it? Unfortunately, we haven't, and even the diagrams demonstrated that there are probes that behave as we want them to behave. In other words, they get data from the ports which are not linked to the service, but their coverage is not that significant. In other words, there is no such thing as a golden probe, a super mega probe. Another question is, where do you get the wide IP addresses for the RUNet? Well, it's a difficult question to answer. We get them from ASN links and announcements of BGP because, it's difficult to define RUNet.
В первом приближении это сделать просто.
At a glance, it seems to be an easy task. You can use UDIP, but technically wise, it's a difficult task.
Можно списаться и...
So we'll get back to you on that. You can email this question to us later on. Another non-technical question. Given the stance of the regulators, isn't it scary to scan the entire RUNET, and how do you go about it? Well, we were afraid to scan the entire RUNET. We're still scared because, you know, various interesting interpretations can come into play. I mean, interpretations of the applicable Russian laws. Igor Pervushin will deliver a separate presentation on these interesting interpretations. However, these activities are not banned. They are not illegal. We do not breach any confidentiality rules, but such activities will still be visible and transparent. Therefore, if you decide to engage in activities like that, well, just keep in mind that you'll be more useful than harmful, but you have to brief the law enforcers on your activities. Oftentimes we get letters saying you will be incarcerated the day after tomorrow for breaching Article 272 of the Criminal Code, but then you start deep diving into that, and you see that the info is already in the foreign ISMs, and no one cares about that. And when someone in Russia starts doing the same thing as someone outside of Russia does, then you get punished. This is a paradox. By the way, if you have any questions from the floor, we'll be happy to take them. Are there any questions from the floor?
Ребята. Пока обязательно тот, кто...
Right. The question about
точность,
the way, about the accuracy and the way we determine it is now
карбон,
the winner. So it's the user is Carbon or the Lexus. You're gonna get a T-shirt as a prize. Thank you for the presentation. My question is as follows: what do we do with the unidentified ports if they don't respond? What do we do? It's a separate story. If you don't get a response from a port and you cannot use a probe,
если этих портов не 100 миллионов,
unless of course there are 100 million ports like that per node, and I'm talking about the blunt honeypots, we can take them out without a banner. Otherwise, we filter them out and only use those with banners. Otherwise, it's just useless knowledge. The port is open, but you cannot use it. So we'll keep a record in the log, but we never even tell the customers about that. These are probably honey traps. Thank you.
Привет, спасибо за доклад.
Thank you so much for the presentation. Hi, everyone. My question is more technical. At the very end, you mentioned that you use project discovery tools. So my question is, how come you use double ROSCAM? Because my research shows that ROSCAM was faster. And I believe, well, Nabo is based on Go build, so in your case, the integration might have been easier. So the question is about the honeypots, and the short answer is a yes. We use Go build and Python. This is the stack that we use. As for the larger projects, we use the Z stack, the Z map, the Z grab, and we also do some contribution to mass scan. We're still looking forward to ZMap releasing its version 4, if I'm not mistaken. Right now it's a release candidate, and we'll send our own patches to the upstream. Geopolitics should be kept in mind. For a Russian developer, it's difficult to contribute anything to the upstream. So we will introduce our changes to mass-scan and ZMap. Thank you.
Еще вопросы?
Any other questions?
Так, ну если вопросов...
Well, if we're out of the questions, then thank you so much for your attention.
Так, еще у меня... В бота? Давайте. Давайте тогда еще вопрос про стек.
Well, there is another question about the stack, because I guess this guy wanted to ask a question about the open source and mass scan.
Давайте просто много вопросов. Вот тоже подходите. Смотрите, давайте, время у нас заканчивается.
We are almost out of time, so please
Докладчиков с удовольствием ответим.
write down your questions in our Telegram channel and ask them offline, because we're going to be here for the rest of the day. Thank you so much. Bye.